If we have the frequency of light of 8.55 times 10 to the 14 inverse seconds, or hertz, what is the wavelength of light? Well, wavelength times frequency is equal to the speed of light. So wavelength is going to be speed of light divided by frequency. So we have 3.00 times 10 to the 8 meters per second for speed of light, divided by our 8.55 times 10 to the 14 inverse seconds. Run that through our calculator, and we get 3.51 times 10 to the minus 7 meters. And for visible light, we often speak in terms of nanometers, and this would be 351 nanometers. So if we have the wavelength of light, 362 nanometers, what is the energy of light? Well, energy is equal to h nu, Planck's constant, times the frequency of light. Well, we solve for frequency up here. We're going to get c over lambda. We substitute down here, so we end up with hc over lambda for our energy of light. But our wavelength, we have to get into SI units, meters, before we can use it. So there are 10 to the 9 nanometers in a meter. Let's see, 10 to the positive 9. So we have 3.62 times 10 to the minus 7 meters. So now we're ready to plug into the equation. Planck's constant is 6.626 times 10 to the minus 34 joules seconds. Speed of light 3.00 times 10 to the 8 meters per second, divided by the 3.62 times 10 to the minus 7 meters, and we will have an energy of 5.49 times 10 to the minus 19 joules. So that would be the energy of a single photon of light. Sometimes we might want to see it in terms of kilojoules per mole. To get kilojoules per mole, we're going to convert joules to kilojoules and then multiply by Avogadro's number. So this is a good answer for one photon. Otherwise, it's 1 kilojoule over 1,000 joules, and Avogadro's number and in terms of kilojoules per mole, we end up with 331 kilojoules per mole. So this is another valid answer for this question.